Hello and welcome back to this course, covering the exam topics for the JNCIS ENT certification. In this section of the course, we're reviewing BGP, concepts, configuration, and monitoring in Junos. In this lesson, we'll review the attributes that BGP uses to select the best path to a destination, and the order in which they are evaluated. We've spent a long time in this course covering the details of link state dynamic routing protocols. The best path selection algorithm for link state protocols relies on the assignment of a metric, or cost, to each link the traffic could traverse in its path to the destination. The algorithm then optimizes the path by calculating the lowest cost path to each destination it is aware of. Those paths are then installed in the routing table as being the best path to each destination. BGP, however, is not a link state protocol. It does not have a map of the network or is aware of any link bandwidths or costs. So let's jump on in and learn how BGP selects the best path for each destination it is aware of. As we've mentioned before, BGP is sometimes referred to as a path vector protocol. This is because BGP uses route attributes that are advertised with each route or destination to determine the best path, rather than some metric or cost based on the link speeds. The attributes that are advertised with the routing information are split into several categories. These categories are based on whether they are included in eBGP peerings between routers in different autonomous systems, whether they are required or not to be included for an advertised route, and whether they are defined as a well-known attribute which all vendors must support, or if they are optional when it comes to the vendor's implementation of BGP. The first category is transitive versus non-transitive. A transitive route attribute is one that is transmitted across AS boundaries, meaning it is included in update messages to eBGP peers. A non-transitive route attribute is one that would either only have significance for the local device or is only advertised to iBGP peers. Next, we have mandatory and discretionary attributes. Mandatory attributes are those which must be included and are required with all route advertisements, whereas discretionary attributes are not required and may be omitted, but may be included if the administrator or vendor implementation of the protocol chooses to do so. The last category is well-known versus optional. Well-known attributes are required to be understood by all vendor implementations of the BGP protocol in order to be compliant with the protocol standards. Optional attributes are not required to be implemented in a particular vendor's implementation to still be considered compliant with the protocol standard. All mandatory attributes are well-known attributes, as you might imagine. Although some discretionary attributes are well known, not all of them are. This is important if you're working in an environment with different vendor devices. Although support for attributes can also differ between models of networking devices from the same vendor. If you are looking to implement routing logic using BGP attributes that are optional attributes, it's important to validate that all of the devices which will be participating in the BGP system support the attribute. Now that we understand the classifications of the BGP route attributes, let's take a look at what attributes are available. This table provides a list of common BGP attributes. There are more, some of which are vendor-specific, though these are the ones we should be aware of in the JNCIS ENT. Although BGP was originally defined in RFC 1105, published in 1989, the modern BGP implementations use the fourth version of the protocol, originally defined in RFC 1771, which was published in 1995. Many additions to the protocol have been published in various RFCs since that time. Many of these attributes are defined in RFC 1771, except for these three. This one, with the double asterisk, was defined in RFC 1996, though many additional RFCs have been published to include various new communities that may be used and their defined uses. These two, with the single asterisk, were defined in RFC 4456 and are used for BGP route reflection. We mentioned BGP route reflection very briefly in a previous lesson. It's used as a scaling technique for iBGP to bypass the full mesh peering requirement. This table includes the name of each path attribute, category indicating if they are well known or optional, mandatory or discretionary, and if they're transitive or non-transitive. Finally, we have the description of each path attribute on the right. The local preference attribute is used to define the preferred path to exit the local autonomous system. This is only exchanged between iBGP peers and is a well-known discretionary attribute, which is non-transitive. If an enterprise is multi-homed to multiple internet service providers, the local preference attribute may be used to influence outbound traffic from the enterprise to the internet providers, to prefer one of the providers over another. The originator ID, like the cluster list attribute, is used in BGP environments where route reflectors are implemented, in iBGP environments. The originator ID is used as a loop prevention mechanism and is populated with the router ID of the router which first advertised the route. If a router receives a route with its own ID populated in the originator ID attribute, then the route will be ignored or dropped. This is an optional attribute, and therefore not all vendor implementations must support it, and it is a non-transitive as it's only used in iBGP environments. The AS path attribute is the attribute that you're likely to see the most in your work with BGP. This is a well-known, mandatory, transitive attribute and contains the list of autonomous system numbers that the route advertisement has passed through. This attribute is also used for routing loop prevention, though this is for eBGP peerings, where the loop prevention comes into play. If a receiving router sees its own autonomous system number in the AS path attribute, then the route will be ignored. The origin code attribute is also a well-known mandatory transitive attribute. It is used to identify the source of the routing information contained in the advertisement. This has one of three values. Either the route was learned by an interior gateway protocol, the exterior gateway protocol, or the information is incomplete, meaning the source is unknown. Moving down, the MED or MED attribute, or multi-exit discriminator, is an optional, non-transitive attribute. To say it is non-transitive is a little misleading, however, as it is only used to influence the inbound traffic sourcing from an adjacent AS to the local AS. The MED attribute may be included in route advertisements over an eBGP peering, though what makes it non-transitive is the MED attribute will not be included in subsequent advertisements of the route to other adjacent autonomous systems. This attribute is used when an enterprise has multiple connections to the same network or internet service provider and wants the provider to prefer one of the connections over another for traffic coming ingress into the enterprise. The following attribute in our table here is the next hop attribute. The next hop attribute is a well-known mandatory attribute. This is the IP address of the next hop to reach the destination. In iBGP peerings, this attribute is unchanged when advertised. This is another reason why an IGP is typically necessary in iBGP environments, as all routers must at least have a path to the next hop in order for the route to be considered reachable. If the next hop is not reachable, Junos will still install the route into the routing table. However, the route will be hidden, since the next hop is not reachable. Across eBGP peerings, the next hop attribute is set to the interface IP address of the advertising router. Since the next hop value is unchanged in iBGP peerings, if a route is learned via eBGP, and then re-advertised to iBGP peers, then typically additional configuration is necessary for the route to be used, since the iBGP peer will need to have a route to the interface address of the eBGP peer in order for the next hop to be reachable. Moving further down, we have the community route attribute. The community attribute is an arbitrary value and can be used for many different operations. Typically, BGP communities are used to perform some logic against a route advertisement. The attribute is optional, though is a transitive attribute, so it may persist in route advertisements across AS boundaries. Route policies may be applied which take certain actions when a particular community is advertised. For instance, some internet service providers allow for enterprises to take action against denial of service volumetric attacks by setting a particular BGP community value that may cause the ISP to either drop certain traffic or to route the traffic through a scrubber to remove the malicious traffic and prevent the enterprise network environment, and protect the enterprise network environment. The aggregator attribute is an uncommon attribute to see in practice. It is used by BGP speakers which perform route aggregation. It is an optional transitive attribute. The atomic aggregate attribute is also uncommon to see in practice. This is a well-known discretionary attribute, so it is not required to be included in route advertisements, though must be interpreted by all vendor implementations. It is used to indicate to other BGP speakers that a more specific route which is included in this aggregate was not chosen or advertised. Finally, the cluster list attribute, like the originator ID, is used in loop prevention when route reflectors are used in an iBGP environment. Since route reflectors are not covered by the JNCIS ENT, we won't go into further detail there. Great. Now let's take a closer look at a few of the common attributes so we can understand their use and purpose a bit better before we review the path selection algorithm. First, the mandatory attribute, next hop. As we mentioned in the previous slide, the next hop must be reachable in order for the route to become active in the recipient's routing table. Since the next hop attribute is unchanged between iBGP peerings, though is changed to the interface IP address of an eBGP peer, one must carefully consider your topology to ensure that the next hop of routes are reachable in your environment to avoid routing issues. Let's take a closer look at the local preference attribute next. Local preference is used to influence the preference of BGP routes, such that the administrators may select which route is installed as the best route in the routing table. This is used to influence outbound traffic from the enterprise autonomous system. The route with a higher local preference value will be the one to be installed in the routing table of BGP-speaking routers. This attribute is propagated only within the local autonomous system. Therefore, it is advertised to iBGP peers, but not eBGP peers. The default local preference value is 100. A particular route to a destination could be deprioritized by lowering local preference value or prioritized by increasing the value. As we see in our diagram below, this enterprise environment has connections to two different ISPs for internet access. The local preference value for the routes coming from ISP B has been set to 90 by a routing policy. Because of this, the routes coming from ISP A are more preferred. Therefore, ISP A will be the preferred outbound network provider. If ISP-A becomes unavailable, if perhaps the router goes down or a link is broken, then ISP-B routes will be used as they are the next highest local preference value. Great. Let's now move on to the next attribute, AS path. As the name implies, the AS path attribute includes a list of all of the autonomous system numbers that this route advertisement has passed through. If all other attributes are left to their defaults, the BGP Path Selection algorithm will generally fall to the AS path attribute, and the shortest AS path is preferred. When we say the shortest AS path is preferred, we mean that the route advertisement with the fewest entries in the AS path attribute is the preferred route advertisement. A route may be deprioritized by duplicating AS path entries in the AS path, a practice called AS path prepending. In this way, the AS path attribute may be used to influence inbound traffic flows by deprioritizing a particular path into the local autonomous system by prepending additional AS path entries. To illustrate how AS path works, we reference the diagram below. For a route advertisement originating from ISP B in AS111, the route advertisement is sent to ISP A, where the AS path only has one entry, AS111. When ISP A re-advertises this route to the enterprise at the bottom, ISP A will include its own ASN in the AS path. Thus, the AS path now has two entries, 111 and 222. Our enterprise operates AS333. If the enterprise advertises the route to ISP B again, it will include its own ASN in the AS path, so it'll have three entries now, 111, 222, and 333. The AS path, however, is used as a routing loop prevention mechanism. Since ISP B should not see its own route advertisement as being accessible through our enterprise, if a BGP-speaking router sees its own ASN in the AS path attribute, then the route advertisement is dropped to prevent a routing loop. Let's now take a closer look at another attribute that is used to influence inbound traffic flows, the multi-exit discriminator, or MED. The multi-exit discriminator, or MED attribute, is used to communicate to a neighboring AS that a particular exit from their AS into the local AS is more preferred. Consider the situation we see in the diagram below. If our enterprise, shown on the bottom, has multiple connections to a single provider, we may wish to prefer one of the connections over another for inbound traffic flows. This can be accomplished without any coordination with the ISP by setting the MED attribute. As we see, the connection on the right is advertising our enterprise route advertisements with a lower MED value, 90 instead of 100. Since it has a lower MED value, then ISP-A will prefer the route advertisement for the connection on the right and send traffic flows destined for the enterprise over that connection. Finally, before we cover the best path selection algorithm for BGP, let's review origin and community attributes a bit more. The origin code simply indicates how the route in the route advertisement was learned. If it was learned from an IGP, then it will have a value of 0. If it was learned from EGP, then it will have a value of 1. If it's anything else, it will have a value of 2. The EGP value isn't really seen anymore. See, although EGP is a class of protocols, meaning exterior gateway protocols, it also used to be a particular protocol itself. BGP is now used as the de facto exterior gateway protocol, and EGP as a protocol is just not used anymore in modern networks. We already know that communities are arbitrary values, which a router can use to perform some logic against particular route advertisements. Community values, however, typically follow the format of AS:community. We can see an example of this down here. Great. Let's now get to the last item for this lesson, the path selection algorithm. In BGP, multiple paths may be known for a particular destination, meaning multiple route advertisements might be received for the same route. Because of this, a deterministic algorithm for determining which route advertisement is selected as the best path must be in place to determine which route will be installed in the routing table. This table here shows the evaluation order of each attribute for a route advertisement. Each item is evaluated in order until a winner is determined. Once a winner is determined, the evaluation stops and no further attributes are evaluated. We have on the right the criteria for each attribute used for determining a winner. By default, the local preference of each route will be the same, so typically route selection will fall to the AS path. If the AS path is of identical length, then the lowest origin code will win. This means routes learned by an IGP will be preferred. If the origin code between the route advertisements are the same, then the lowest MED will win. If the MED is identical, then route advertisements learned from an eBGP peer will be preferred over routes learned from an iBGP peer. If the routes are learned from the same type of BGP peer, then the IGP metric to the next hop will be used, with the lowest metric cost of the next hop winning. If the IGP metric is the same, then the route which is currently active will be preferred. And if no route was active and the two advertisements were received at the same time, then the shorter cluster length and lowest peer router ID will win the selection. And that's it. I appreciate you working with me to review the BGP route advertisement attributes and the path selection process. I hope that this lesson has been informative for you, and I would like to thank you for viewing.